At first glance, there are many different types of anesthetic machines, from the most sophisticated to the simplest ones, some of them even being portable. However, they are basically made according to the same scheme. Still, the essential part of every anesthetic machine is the source of medical gases. The gases are usually oxygen, nitrous oxide, and air. They are delivered either from cylinders or from external tanks. Their mutual non-exchangeability is ensured by various means. The cylinders are of different colors and of different thread diameters. Pressure regulators are used to decrease the pressure of the compressed gases to a safe level. The thread is different for each gas. The pressure gauge indicates the pressure in the cylinder. External tanks supply gases for hospital pipelines. In pipelines, the pressure at outlet is already reduced, so no pressure regulators need to be used. The machine is connected to pipelines by quick couplings. They're also color-coded and have a different shape of the couplings to avoid a mistake. The dosing devices for gas anesthetics are flow meters, glass cylinders which widen upwards. The level of gas flow in liters per minute can be read on the calibration scale against the upper level of the indicator. Volatile anesthetics are supplied by high accuracy vaporizers. A sophisticated construction of them enables to keep a constant concentration of the volatile anesthetics independent of the surrounding temperature. Each anesthetic has different physical properties, mainly the boiling point, and so vaporizers cannot be interchangeable. The non-interchangeability of the contents is ensured by different shapes of the connectors and threads on bottles with liquid anesthetic of each agent. In case of emergency, there are bypasses on the machines which, when switched on, provide high level of oxygen into the inspiration mixture without regard to the levels set on the flow meters. From this moment, all anesthetics form a mixture either as gaseous anesthetics or as vapors of the liquid anesthetics, and they are administered to the patient. The patient is connected to the anesthetic machine by an anesthetic system. The oldest systems were constructed so that the inspiration and expiration went to the atmosphere as with the Schimmelbusch mask. The mask was filled by a tissue and the anesthetist dropped ether on it. These aids cannot be used for novel anesthetics, and so special devices are used. The basic system for anesthesia of adults is a breathing circuit. It consists of an expiratory and inspiratory limb, which are separated by two one-way valves. The system contains also a bag, which is used as a reservoir or can be used for manual artificial ventilation, a carbon dioxide absorber, and an adjustable pressure limiting valve. A sterile circuit is used at the beginning of the day's theater list. A nurse checks the functioning of the one-way valves and the absence of an air leak. While the machine is used, you can easily see how the valves are functioning. We measure the expired volume by a volumeter and the pressure in the circuit by a manometer. Carbon dioxide absorber is filled with soda lime. Soda lime is used as it absorbs carbon dioxide and it is partly able to regenerate. This is shown in the third equation. During the reaction, heat and moisture are produced, helping to warm up and moisture the mixture to be inspired. The exhaustion of the capacity of the absorber is signalized by a color change. This agent turns blue, others can turn, for example, pink. The advantage of the breathing circuit is that we can use a lower fresh gas income than the patient's ventilation per minute. It preserves heat and moisture, which would otherwise be lost. The consumption of anesthetics also decreases, causing lower pollution to the surrounding environment and lower costs. The resistance of the breathing system, which it exerts during spontaneous ventilation, can increase muscle work, and with small children it can lead to exhaustion. In pediatric patients, one-way systems are used where there are no valves and expiration and inspiration are separated only by fresh gas inflow, exerting a minimum resistance to breathing. The best known type of such system is the Anaesthetic, which can be used even in the smallest babies. During expiration, the expired gas is washed out by fresh gas mixture to the expiratory lymph. During the expiratory pause, the expiratory lymph fills with fresh gas, and during inspiration, the patient breathes in not only from the inspiratory lymph, but also from the expiratory one, which serves as a fresh gas reservoir. The expiratory lymph must be long enough to ensure that the inspired gas is not diluted by atmospheric air, and the fresh gas flow must be high enough to wash out the expired gas and to prevent rebreathing. In practice, normally such fresh gas flow is chosen that corresponds to approximately 2.5 times the patient's minute ventilation volume. With the classical Anaesthetics, it is difficult to monitor ventilation and to perform artificial ventilation. That's why modifications are used which are supplemented with a reservoir in the shape of a bag, which makes it easier to monitor the spontaneous breathing and provides for easier artificial ventilation performed by hand. The most common modification is by Jackson-Rees, its special feature being an open-ended bag on the expiratory part. Here you can see the Jackson-Rees system. The arrows show the inspiratory lymph, the connection to the face mask, or another means of management of the airways, the expiratory lymph with an open-ended bag. Jackson-Rees system is used in pediatric anesthesia during spontaneous and also artificial ventilation. To perform artificial ventilation, the open end of the bag is occluded between the fourth and the fifth finger, and the bag is squeezed between the thumb, the index finger, and the middle finger. Another open-ended bag is the Kunz system. There exists also the possibility of using a valve which obturates the expiratory part as opposed to the manual way by Jackson-Rees system. Theoretically, it's a different type according to the established classification, but the use is basically the same. Another type of one-way system is the Bain system. The inspiratory part leads through the inside of a larger tube through which the patient breathes out. The course of breathing is similar to the air steepies, but at the expiratory ending there is a reservoir with a pressure valve which allows artificial lung ventilation. The Bain system is used for children as well as adults. The disadvantages are similar to the other one-way systems, but its advantage is its comparable compactness and the possibility of it being very long and still without the danger of rebreathing. Moreover, it may be connected in a great distance from the machine. This is mainly advantageous when there is a substantial distance between the patient's head and the machine, as for example during the examination in the magnetic image resonance tunnel. Otherwise, the Bain system can be used also for common instances of anesthesia while maintaining spontaneous ventilation. An interesting system with a partial rebreathing is a system according to Waters with an original Czech modification by Drabka. The system is equipped with carbon dioxide absorber. The outflow of the expired gas in Drabka's modification is done by a tube which is submerged underwater. To prevent bypassing of the breathing mixture, the entire space of the container must be filled with the carbon dioxide absorber. Waters' system may be used in small babies, enabling even to monitor ventilation by capnometer. The next parts, which are very important and according to which anesthetic machines are classified into various categories, are the accessories. The basic equipment is a suction device, and the most important, a ventilator, a device used for artificial pulmonary ventilation. Anesthetic machines can be divided into three basic categories according to their quality and gas leakage. Standard anesthetic machine, where the minimal fresh gas flow is 4 liters per minute. Low flow anesthetic machine, where the minimal fresh gas flow is 1 liter per minute. And minimal flow anesthetic machine, where the minimal fresh gas flow is half a liter per minute. Low flow and minimal flow systems are patient and environmental friendly. Their disadvantage is a higher price, which is compensated by lower payments for anesthetics. The fresh gas flow in standard anesthetic machines is not only expensive but may also cause environmental pollution. To prevent health hazard for operating theater staff, scavenging systems are used. The devices used for administering inhalation anesthesia passed a long way from simple aids to sophisticated electronic machines. However, the safety of any anesthesia is done not only by modern equipment, but has always been and will be primarily a matter of education, skills, and vigilance of anesthesiologists.